So number 29, we have a metal rod that's force moved with a constant velocity v along two parallel metal rails connected with a strip of metal at one end. The magnetic field is 0.35 teslas and it points out the page. A, if the rails are separated by 25 centimeters and the speed of the rod is 55 centimeters per second, what EMF is generated? So for A, first thing we're going to do here real quick is to define a new distance x up on top here. Not that it's critical, but now I can identify the flux. The flux is, of course, magnetic field times the area. In this case, the area is going to be L times x. Um, why is this interesting? Well, remember the EMF generated is the change in magnetic flux over the change in time. In this case, B time, or the derivative of that magnetic flux with respect to time. In this case, magnetic field and L are constant. X is what's changing with respect to time. So of course that's just BLV. Plugging in our numbers, again remember converting centimeters to meters, we get these, and that gives us an EMF of this many volts. Next question. If the rod has a resistance of 18 ohms and the rail and connector have negligible resistance, what's the current in the rod? Well, for B, we're just using Ohm's law. Plugging in the voltage we just found, or the induced EMF, divided by the total resistance of the circuit, 18 ohms, gives us a current of that. Finally, in C, it asks, at what rate is energy being transferred to thermal energy? If you think about rate of energy being transferred, rate, it's the change in energy with respect to time. In other words, what are we asking for in this case? Power. Now, I could use any power equation you want. We've got both voltage and current. You could have done just I times V, but I always like using I squared R for when I'm thinking about energy being dissipated in a circuit. In this case, plugging in the current we just had, the resistance of the circuit, 18 ohms, you'll get the power being dissipated is 0.000129 watts. Hopefully this makes some sense.